Welcome, everyone. We're going to give it about 20 more seconds while folks filter in, and then we'll go ahead and get started. All right. In the interest of time, we're going to go ahead and get started. Thanks so much for everyone for joining us. Hello and welcome to Fresh Energy's webinar featuring new energy codes and what they mean for residential and commercial buildings. My name is Ben Rabe. I'm the Director of Building Performance at Fresh Energy, a clean energy nonprofit in Minnesota. Now, a few housekeeping items before we get started. We'll be taking questions at the end of the webinar, and I want to remind you to use the Q&A button at the bottom of your screen to submit your questions. Try to avoid using the chat function. I'd like to keep all the questions in one spot for when we get to the Q&A portion at the end. You'll be able to see each other's questions and upvote the ones you like. Next slide, please. I'd like to take this opportunity to introduce our guest speaker, Don Sivigny. Don is a state energy specialist and senior code representative at the Minnesota Department of Labor and Industry and has led the department's work on several code updates. Next slide. Today, Don will address changes to the commercial energy code as well as the process and potential for updating the residential energy code. He'll be covering a lot of material, but remember, you can submit your questions at any time throughout the event. I also want to recognize Greg Metz and Steve Schold, Don's colleagues at the department, who also work on energy codes, who can be a resource for you as well. With that, I'll pass it over to Don.
Well, good morning and good early afternoon, everybody. This is Don Sivigny. Yeah, Ben mentioned two other individuals, Greg Metz and Steve Schold. Both are colleagues of mine at the department. I've kind of changed my position a little bit at the department. I'm still going to be working on energy code for many years to come with those two gentlemen, but Greg is going to be taking the lead on the commercial for the future here as we move forward on the commercial codes, and Steve Schold is going to be working with me, and he's going to eventually take over the residential things as we move forward and kind of transition into somebody else having the full understanding of things as well for both of these two documents, and so that we have backups and things such as that. I'll be working with them in the years to come as well, but slowly we'll be transitioning more and more of that over to them, and I look forward to that opportunity and giving them an opportunity to jump in and get involved with this as well. I know Greg's listening in. Steve had a previous commitment and couldn't, but he is going to go watch the webinar afterwards. So I think we'll kick this off and get going. We'll start with the provisions here. We're going to start on the commercial provisions of the code. And I apologize for this having to be so late in the game here on this. I meant to do this earlier with Fresh Energy, and some of you may or may not know, but due to a family emergency, I had to leave the state and go tend to my son out east. And so we rescheduled it for today, and I appreciate your patience and your waiting for this class to get taken on and worked through. So we'll start with the commercial provisions. Beginning in March of 2020, the Department of Labor and Industry, we had adopted and switched to the 2020 version of our codes using the 2018 International Energy Conservation Code. And of course, we have Minnesota amendments. Now, what we do is we exclude Chapter 1 on administration in pretty much all of our codes because we have Minnesota Rule 1300 that addresses the administration and enforcement of the state building code. That takes place of all the Chapter 1s in most of the codes. The exception to the energy code is that there's a provision in there in their administration chapter that addresses additions, alterations, renovations, and repairs. We did keep that language from the IECC code in the front of both the residential and commercial energy code. The commercial energy code is still considered Minnesota Rules Chapter 1323. We adopt things under the rule format, and we adopt the residential energy code as 1322, and the commercial energy code is Chapter 1323. We just update those chapters with new versions of the code from periodic timeframes. The 2018 IECC also in the document itself in section 401.2 allows the designer and builder to utilize ASHRAE standard 90.1. Currently, it's the 2016 version as an alternate to the IECC. So you can use either the IECC or the ASHRAE. If you choose the IECC, you as the designer or builder need to use that document in its entirety. If you choose not to use the IECC, you can use the ASHRAE standard, and that has to be used in its entirety. You're not allowed to trade off between the two documents anymore, as we used to several years ago, be able to take a provision out of one and a provision out of the other and use them for the same building. It just doesn't work that way anymore. The methodology and how the research is done just doesn't allow that anymore. Underneath federal law, we as a state are required under the provisions of federal law to review the ASHRAE standard 90.1 1989 or its successor standards as they become published regarding energy efficiency in commercial buildings. So we are required under federal law to do a review of every ASHRAE standard that comes out to determine whether it's a standard that we will look to move to or not through our rule process, through the adoption process where we use tag committees and things such as that. On February 27th, DOE issued a determination saying that the 2016 standard would achieve greater energy efficiency by about 8.2%. That's important because if they came back and said that it does not determine a greater efficiency, then the states aren't obligated to do a review and adopt. So once the determination is made that it would achieve greater, then we have a time frame that we are bound by to review and adopt, or at least review and let them know whether we're adopting or not and why we're doing it or why we're not. On April 21st, 2021, they issued the determination on the 2019 standard. And so that's where that time clock on the department reviewing things and what would happen there as to adoption of that document took place. On May 28th, the department will be presenting a report to the Construction Codes Advisory Council about that review of ASHRAE Standard 90.1 2019. Greg Metz chaired the Technical Advisory Group or TAG Committee, and they will be providing that to the Construction Codes Advisory Council for their consideration on energy for commercial buildings in the future. DOE does not do any official determination on the commercial provisions of the IECC. And so they look at just the ASHRAE standard. They don't do a report, an officially report on the IECC. So we're following federal law. They estimate the national savings on commercial energy codes for the 2018 with an 8.2% energy cost savings. Energy cost savings are when the buildings save energy, the costs are lower to generate energy. It saves on life cycle of equipment, transmission lines, and many other things that the more you put product through them, energy in this case, the more wear and tear it has on them. So by reducing energy use and those energy costs, they can now reduce the life or increase the life cycle of the equipment by reducing the energy use. There's requirements for source energy. Cost of technology has been reduced to provide off-site and on-site options for things such as renewable energy. Things such as solar, which is becoming very popular and has grown dramatically as you drive around the state of Minnesota and the country, you see more and more solar fields, a lot of times owned by utilities and other things that are feeding into the grid system of the area that they provide electrical service to. And so that's another thing that has increased quite a bit. And then the one that we, from a code standpoint, we really kind of go by are site energy savings. These are the actual savings that are for each specific new building and based on the new codes and the new technology. For instance, envelope tightness and the efficiency of the envelopes. You know, creating a tighter building envelope does create energy savings. We understand of the fact that tighter building envelopes may require some additional ventilation and things, but all that is considered in. Lighting controls. You'll see that there's changes coming in lighting controls for offices, hotels and motels, especially the suites where we can have one place that shuts all of it off when they leave that suite for the day. You have one switch to shut off that shuts everything in that unit off, TV and all the lights and everything such as that. Daylighting. Daylighting is a big thing in commercial buildings. We'll talk about that and bringing in natural light so you can reduce the amount of artificial light you have to produce through luminaires and other things. Equipment efficiencies. We've seen a huge increase in equipment efficiencies in the past, and we're going to keep seeing them as manufacturers work harder and harder to create more efficient equipment. And then a big one that probably gets missed is proper equipment sizing. Oversizing of equipment, especially on the air conditioning load, is an extremely high cost in the fact that you're not running that equipment efficiency. And so the changes to the equipment have changed so that we now have maximum oversizing that's allowed. And so making sure we're actually getting the proper equipment into that building and sized effectively is a very important part of energy saving. Some of the changes we're going to talk about today is in the Minnesota Commercial Energy Code. We're going to review them and we'll kind of go through them as we get through here. Some of them may be kind of confusing. We talk about substantive and quantitative and all this, but we'll try to make it pretty simple and put it into some general terminology that everybody understands. There are not very many substantive changes, probably less than you think, actually. Some are simple changes to the section of the code that don't really have to affect the code language itself at all, but they might be for formatting and things such as that those changes happen at the national code level where somebody believes we don't think that should be in this location, it should be in this location. We didn't change what the code says, we did change the location, but it is actually a code change. And we look at that national document from that standpoint. When we get into change or use and occupancies, there are some references to tables and sections that are revised to coordinate with numbering changes made to the 2018 IECC. As we start adding code changes or adding code language to the code, the numbering ends up changing. So we've seen that in several instances through this document as well. ASHRAE addresses changes in use or occupancy as an alteration. And then it sends you to section 5 as it relates for insulation, air leakage, air penetration products, and for other portions that are being altered. But it is only for the portions that are being altered. If you don't open up the wall, there's no requirement in the code for you to bring that up to code. The code is typically not retroactive. We have low energy buildings. We have previous amendment to this, and we've been able to remove that amendment due to the fact that a repealer is when we remove an amendment, that the requirements for low energy buildings are now located in the IECC in section 402.1. For low energy buildings with ASHRAE, they divided into 3 different groups essentially. You have conditioned assemblies for both commercial and residential occupancy, and then they add unconditioned assemblies and then they add semi-heated buildings. So you can have a building that is greater than 3.4, you can use 3.4 to 20 BTUs, and that's what we would call a semi-conditioned building in the code now, but that's only in the ASHRAE code. The IECC doesn't have that. This is why you need to pick a document and stay with that document. The 2012 did not specifically in any way address greenhouses. They were kind of the odd duck building that was out there. Nobody knew, do I have to enforce the energy code? Do I not have to enforce the energy code? That question came up an awful lot. And how do you enforce the energy code on a structure such as a greenhouse? That's been cleaned up in that greenhouses are now in the code and they're listed as exempt. So they put them in the code to tell you don't have to follow the code, just to clean that up so that the questions would go away and everybody would be on the same page. There's a lot of changes in information on constructional documents. There are a lot of details have been reformatted in the format of a list of sub-items. And the reason we did that in the codes is to make it easier to use. We want to make the code less complicated, more understandable, and make sure that everybody can come to the same conclusion as they read it. They've added some sonars. G, L, and N are the new details. We'll kind of talk about those here. The first one is on fan horsepower. It's required to add a fan brake horsepower to the fan equipment itself on any fans that are greater than 1 horsepower in size. And this is going to help us as going to guide the designers to choose their fans that they're using in these systems very wisely. And again, preferential treatment for efficiency would be given to probably the variable speed and direct drive fans, as they do save substantially more energy. We talked a little bit about daylighting. What is daylighting? Daylighting is using the sun's natural light to light the area of space. And on commercial buildings that are typically operated during the day, and some are at night, but the majority are daylight hours, we can utilize that sun's light, the light ray from the sun. It has a heat ray and a light ray. We can utilize the light ray to light the building where we don't need to provide artificial light from an energy source that typically is using a fossil fuel like coal, oil, natural gas, things such as that. And now we actually have a secondary zone. We had originally the zone 1. They've now done the research and found that they can add a secondary zone in here that is not as much light as zone 1 as you see in the drawing here, but does provide light at a little bit of reduced rate, and we can calculate that in, again, saving energy. Daylighting is the controlled emission of natural light into the building to reduce electrical energy costs. It saves us energy. And again, the sun's got a light ray and it's got a heat ray. And the heat wave that the light or the sun sends out, that's where our windows get involved with our fenestration products for heat reflectiveness and other things like that. They're letting the light ray through, but they're not letting the heat ray through. Additional details are that they've added sub-item N, and this really gives the building official something because it says the building official can request additional details. We have had cases where a designer is not following the prescriptive approach of the code, and they're not absolutely using 100% one of the performance options. It's kind of a something in between. And this gives the flexibility in the design of that building to the designer to work with the building official and come up with something that's efficient and accommodates the needs of the building owner. And what happens though is that the building official may have questions, and we've had times where they said the building official, you don't need to know that. Code doesn't say you need to know that. So they've added something in there that says the building official can ask for additional details right into the documents themselves. There's a lot of grammatical changes that are made to the sonar. They're not necessarily changing the code or modifying the code, but they're there for grammatical parallelisms and will provide clarity to the enforcement of the code. There's changes to the definition section of this document. Air barrier construction. The difference between the 2018 and the 2012 IECC, the previous code we were was the 2012, are that the air sealing of penetrations, we're providing additional guidance for sealing around a very specific item, fire sprinklers. There was really never anything in the code to address these, and the fact that you've got to be cautious when installing different things around these sprinkler heads to make sure that we're not impairing that head at all. And so they put some very specific things into the code for that. ASHRAE does not define it other than to say that in the section 543 of the code, they give you 3 options on air barrier requirements for the building. There's a continuous air barrier design. You've got to provide in your design a continuous air barrier and show where that is. And there's 4 sub items that are in there to provide you some of that guidance. There's the installation of a continuous air barrier. So this is something that a building inspector would see on site. And there's 5 sub items there that they would be looking for at that point in time. You probably could use both of these. The designer's going to design things. And then when you're in the field, that's part of the plan review, the continuous air barrier design. But when you're in the field, that's where the installation or inspection of that installation comes into play. There is another one out there, and that's for testing of acceptable materials and assemblies, which this requires a whole building pressurization test. We all know about blower door testing and things in residential buildings and commercial buildings, but you get into some of these buildings that are huge in size and multi-stories. How do you pressure test this building? There are ways to do pressure tests on the entire building, but some of them with the different wings going out, can you test part of it? How can you do that? This gives you some options to do that. There's some provisions in the building envelope and design requirements for stairways and shafts. We repealed this because both the 2018 International Energy Conservation Code and the International Mechanical Code have both been revised, and they include damper requirements for stairways and shafts as well. In the Energy Code, it's in section 403.7.7, and these are now changed to mandatory requirements. So you have prescriptive requirements, you have performance requirements, and you have mandatory requirements in the code. The mandatory have to be applied to both prescriptive and performance options of the building. There's requirements for the outdoor air intakes and exhausts as well. This one, again, we repealed due to the fact that it's in section 40377 of the code. And there's also provisions of it in the mechanical code. And again, they are mandatory requirements. So you have to do them no matter which version of the building you want to build, prescriptive or performance. Heating and cooling of vestibules. We have an amendment to this one currently in the current code. We've changed the temperatures there. We've risen them some to address the issues of the freezing that happens in Minnesota climate conditions. If you've ever gone to a retail store or something like that where they've had a vestibule, you get there and the door is having issues because it's getting warm, moist air coming out, hits the cold surface out there and freezes. So what we've done is we've raised the temperature of that to allow for more heat to be out there to reduce the amount of freezing that happens. The other thing, and the question that I get often, and especially in today, is that when do I not need a vestibule? Well, if your door, your front entry door of the building opens up to an area that is sectioned off by doorways, not openings, just doorways that close, and 3,000 square feet or less doesn't require a vestibule. So there are some exceptions in the code to that. And that's for our climate zone again as well, to again address the freezing issues. There's requirements for minimum pipe insulation in the code. The proposed language modifies a footnote in the code and clarifies that it's not required to have pipe insulation on a radiant heat system. Now, you would think that would make common sense. We have a radiant system. We want that radiant system to release that heat and keep that floor warm or whatever it may be. Maybe it's above heating downward. Why would we insulate that pipe when the design is to allow that heat to go off? Well, the code didn't say you had to, you could delete it from there. Most people did, but there were some that didn't. So there was a change that was put into the code to very clearly in footnote D tell you that you don't need it if it's a radiant system. Pools and spas. We have a lot of discussion on pools and spas. If you have a spa such as this or a pool, and how do you, one, retain the heat on that pool or spa that's being heated? And then two, how do you retain the vapor that's coming off there? Because heat coming off there, of course, is going to require more cooling of the water or heating of the water. And if the water evaporates off there, you've got to now add more water, which is typically cold water that has to be heated up. And so the code addresses that the vapor retardant cover is required on pools and spas unless there's an exception for that out of the code. So this one here, the exception here says is modified to increase the percentage of site recovered energy. From 70, we went to 75%. So pool receiving 75% of its energy for heating of the pool from something that is site recovered, such as solar or something else, then you can, the exception here says you don't need to meet this provision of the code. Now in this picture here, we would look at this as three separate pools. 1, 2, and the little kiddie pool over here would be 3. And so you would have 3 separate covers, and you would look at each pool and see what that's getting its energy used to heat that pool from. If each of these pools is getting 75% of it from a solar array system, then you can omit the cover. If one of them isn't, that one's going to need the cover. The effective date of this code is March of 2020. So we're a little over a year into it, and it's been going very well. I think people are getting on board, they're catching on. They spend a lot of time with the codes and looking at them. Our process is very effective and how we do things is very well thought out. And there's a lot of input into this from everybody and anybody who wants it. So we usually have a pretty good code, and we haven't had a lot of challenges to this, just some clarifications mainly. That wraps up the changes for the commercial provisions. Residential provisions we'll get into next. Residential provisions are for the residential energy code, which is, 3 stories or residential occupancies, 3 stories or less in height. You get above 3 stories, you're now getting into the commercial provisions of the code. So you could have an R1 apartment that is 3 stories in height, that would be meeting the residential energy code. You would have an R4 apartment that is 4 stories or more in height that would meet the commercial energy code. And so you have to look at the definition of residential buildings on the energy code, which explains that. And then from a standpoint of what is a commercial building, we simply said all buildings not determined as residential. And we've done that in our codes for years. And recently we took this to the national code committees and submitted our definitions for residential and commercial to the national committee and how it clarified things, and that was accepted into the national code. So Minnesota is very active and very respected in the provisions of code adoption at the national scene, and we've got a lot of things into the code that are started as Minnesota provisions. Under federal law, there's an Energy Conservation and Production Act. It says the Secretary of Energy needs to review the International Conservation Code and make a determination as to whether the updates would improve energy efficiency in residential buildings. So Pacific Northwest National Labs, PNNL, is typically the agency or the laboratory that is used by the Department of Energy, DOE, to make their determination on percentages. And you'll see a lot of numbers coming up in the calculations that they do. That determination basically is used as a useful guidance by state and local governments as we review and update building codes. It's valid information, it's third-party done, and we use that as what we're looking at to what our energy savings and things are. And there's become a lot of energy savings on the residential sides of buildings. The most recent edition for the 2018 code was published in August of 2017, triggering the DOE review, and Pacific Northwest Labs did that review, and they found that preliminary analysis that the energy savings based on the 2018 residential provisions were relative to the previous energy code in the 2015, that they were there and that we needed to move forward. So we're going to go through some of those things in this document on the methodology they use so that you can have a good understanding of where this comes from. Very similarly, this was done on the commercial side as well. Many of the changes don't have a direct impact on energy efficiency. So then they're not designated as falling into one of the two categories that we're going to talk about. There are changes that affect only procedural aspects of the code that happened, such as those providing guidance on inspection protocols or on modeling, different rule sets for those. Those aren't considered. Changes where impacts are captured under a complementary code requirement. The relationship between air tightness testing, and all those associated thresholds, along with sealing of equipment and appliances and penetrations and all that, there serves kind of a double. So we try to avoid that, and we count it in the quantitative analysis. Changes that are targeting non-energy aspects of the code, such as water efficiency requirements. Those aren't counted in their analogy as well. And then administrative changes, including editorial corrections, the reordering or renumbering of the code, putting it in a certain order, moving things around. Clarifications in the code may not change the code language. We just added a few things to be very clear as to what that is. We did not change the intent of that section, but by adding some wording, we cleared up the intent of it for people to understand how to enforce it. And then anytime we had reference updates, if you're going from the 2016 ash rate to the 2019 ash rate, that's a code update. Sorry about that, but I shut that down. So we don't include those in there as well. The analysis is a combination of both qualitative and quantitative components. Those are the two ways that they look at this. It's to identify changes that have a direct impact on energy efficiency. As we talked about, there's a lot of changes that don't have a direct impact. The qualitative ones are the ones that do have a direct impact on energy savings in a significant portion of residential buildings. You may not have that exact same savings in every building depending on the specifics of that building, but overall on average in a substantial number of them, you would, and that's what it's based on. Quantitative is a filtered changes that retain only those expected to have a direct impact. And then we have to be able to reasonably quantify them through energy modeling and energy analysis. Of the total 47 changes that the ICC approved at their hearing for the 2018 IECC, 14 changes have a direct impact on energy use in residential buildings. 11 are expected to reduce energy use, and 3 are expected to increase energy use. Now, some people find that to be a little bit of a funny thing because we passed codes that said we're going to allow the increase of energy use. Sometimes that's better. The vestibule that we have in Minnesota, that changed there to increase the energy use of that vestibule, increase that temperature a little bit, add substantially more good qualities from a life safety standpoint, that if somebody's trying to get out that door and the doors are frozen and not operating, you're going to start backing people up in an emergency. And so sometimes we will do that. And that's because they typically will give up an energy thing every time, saving a little bit of energy to increase a life safety thing. It's just, there's just no comparison to say, look, we're going to save a few dollars here, but we're going to injure or have other things happen to several people. That's just not how we want to do things. There were 33 additional changes that are administrative or have no impact on energy portions of the code. They're all the non-energy portions of the code. Again, renumbering, clerical things, different stuff such as that. So of the 47, 30 were administrative, 3 were not energy related, 3 increased energy, and 11 decreased energy use. As you can see, now we would have done this 10 years ago as the codes have progressed. The increase in efficiency is getting less and less until new technology is developed. And as new technology is developed, then we can increase that efficiencies again, typically. But at some point in time, we run out of these big jumps of energy efficiency increases because technology hasn't caught up with us. And so we're still increasing energy and percentages are still good, but we are seeing each year as those things tend to drop a little bit. Of the changes characterized that have direct impact for new homes, only 2 are expected to have a significant change on those new homes. One is window U factors. Window U factors are the calculation of energy loss through the window system. And the code is currently at a 0.32, or was currently at a 3.2. It is now down to a 3.0, which is a jump in savings for them. The other one is high efficacy lighting, and seeing the fact that we're using better lighting fixtures. You know, we went from incandescent bulbs to fluorescent to LEDs and other units of light that actually are much more efficient. If you take a 60-watt incandescent bulb, it's about 13, 14 watts in a fluorescent. You get it to an LED, it's maybe 1.5 watts or 2. So there's a significant energy savings there. And those are the 2 main ones of all of these changes that actually were warranted to have a further quantitative analysis done on them. We are using currently the 8 standardized climate zones. These are the climate zones that were in the 2012 code, as well as the 2018 IEC and the accompanying ASHRAE standards for them. However, their ASHRAE, this is an ASHRAE table, and the ASHRAE table is going to be changing. You can see this in the first map here. The red line is the previous or the current code in Minnesota for climate zone separation. Anything above the red line is actually climate zone 7. Anything below the red line is climate zone 6. The TAG committee is reviewing and going to be working with the Construction Codes Advisory Council on the new climate zone map. This is for commercial buildings only because it's in the ASHRAE standard for 2019. It's not yet in the next standard, that would be the 2021 standard for the IECC, as we haven't gone through that adoption on that document yet. But there's 7 different counties that are changing from from northern zone to the southern zone. And then down in the southern part of the state, the national map has 3 counties that would actually could be considered in climate zone 5, but the numbers are so close that this committee, I think, is choosing to probably leave them in the climate zone 6. There was discussion on that, and I think, Ben, you were part of that as well. And so, but we're going to see the climate zone map change here. And so we'll start seeing some efficiencies that are going to be a little bit better because we're going to be accurately representing what the climate zone is there. So as we split this out and look at this for its energy use, in the 2018 IECC. We look at it by climate zone. And this is from the research study that was done. And so there's 8 climate zones and then a national average. We are not in 8 of those climate zones. Currently, we're in 2 of those climate zones. And it has things, it has a weighted percentage that it adds, site, source. And the one that we look at really on the residential side is the energy cost residents per year. We know that, this is based on normal conditions, normal heating. We can't control somebody cranking that heat up to 95 degrees because they're cold. That home certainly is going to use more energy, but it's based on an average of about 70 degrees temperature in the home. And it's based on the climatic data that we have in our climate area as well, and our air freezing index temperatures and all these other things. And so in the Minnesota version, for climate zone 6 and 7, which also could include other states as part as, Wisconsin and other northern states and Michigan and the Dakotas and things such as that the average on the climate zone 6 energy cost per year is about $1,200 in a residence, typical residence that they modeled for climate zone 6, and it's $1,551 in climate zone 7. So when we break that down even further, in the 2015, it was $1,225 and $1,582. So we've got roughly $25 and $31 difference or savings in each of these buildings. Now that may not seem like very much. So I'm going to say 25 or 31 more dollars a year on my energy bills, but multiplying that times the number of new homes that are out there that are being built and things such as that, as we see the market is just flooded crazy today with new construction. And as fast as they build them, they're sold. And so you start adding that up, multiplying it out times the number of homes, it can become a substantial number. The qualitative assessment was done. We'll go through these. I want you to understand how the graph lays out. We're again incorporating those things that have direct effect on energy use. We'll show some information for each change here. There will be a proposal number at the very beginning, then a code section, description of what that change is, its impact on energy efficiency. Is it included in the energy analysis? And then a short discussion. And then I've added some information there on Minnesota and what we've done there. The first one is its code change was RE17, Green Residential Energy 17 in the 2016 code hearings. It exempts log homes designed in accordance with the ICC 400 standard for thermal envelope requirements. Now, I will tell you that I've sat on the standard for a while. Those folks, and we are working very hard to get efficient, energy efficient log home buildings, even increase that efficiency every day. And so we move forward with that as to have the national codes. It allows substantially less efficient walls than the IECC does. So this could increase energy use by having log homes not meeting the provisions of the code, but it's relatively a small portion of our housing stock, roughly about less than 0.5%, about 0.4% of new homes. It's not a featured typical home in the state or in the country, but there is a very specific clientele and a very specific builder group that does build these across the country and across the state of Minnesota. Minnesota code currently requires a minimum of a 7-inch diameter log. Nothing less can be used. Now, we adjusted that due to the fact that in Minnesota, to use a Minnesota log with our climate conditions, we have a much shorter growing season. And for our builders and log home builders and our log home industry to compete, we have to make some of those adjustments. And so it's similar to the ICC 400 standard. However, Minnesota did go even further into efficiency and say that we're going to increase the U factor of windows, meaning lower them. Increasing a U factor means you're making it better. So a lower U number, the better the number, the better the window. Opposite of what an R value is, the higher the number, the better the product. So we went down to a 0.29 overall U factor and have been at that for several years, and the code allows a 0.32 at that time. We're going to be going, the code's going to be going down to a 0.30 eventually here. We'll still be better than the code in this aspect now. And so we've worked with that log home industry, has done a fantastic job to participate in this in Minnesota and across the country. We've had meetings with the people in Minnesota to meet with them and see their designs and see what they're doing different. And this is how we came up with these numbers. The next one says that's RE22. It says it requires an R5 insulation under the entire slab line grade when the slab is heated. Now, this should decrease energy use. This wasn't one that of the two that we actually took on and looked at again with further analysis, but it reduces heat loss with heated slabs especially. It's decreasing the energy use because what's happening is those heated slabs, if you don't have insulation under the heating system, the heat goes down into the earth and really doesn't do any good for this floor system. And so by having the energy go up, installing insulation under that to force the energy to go the opposite direction, that slab stays heated at a greater temperature. The heat system doesn't have to kick on as often to keep it at a temperature, and it does represent a lot of energy savings. Manufacture these heating systems already under the provisions of their installation requirements have been asking for this and requiring this as installation instructions for years. It's been placed into the code, so now it's now in 2 locations. The code says you need to follow the code and the manufacturer's installation instructions, whichever is the most restrictive. In this case, these are going to be identical. So it's going to keep the heat in the slab and not allow it to go into the earth. So it's really not a change for what we've been seeing, but it is a change in the code by adding the language to make sure that if for some reason a manufacturer said you only need an R2 underneath there, the code's more restricted, it's going to say an R5. One of them that we did look further at is that window U factor. Again, adding better U factors to the windows reduces heat loss or heat gain through windows and doors, decreasing energy use. This change is going to affect 6 of the 8 climate zones in the United States. Minnesota builders and homeowners, we recognized this many years ago. We've seen our builders and our homeowners request better windows. We've seen our builders provide better windows. Right now, on average, we're seeing anywhere between a 2.7 and 2.9, I would say. I have seen some as low as 2.4 and 2.6, that they're just buying, better windows, triple pane windows. You see the advertisements on TV and stuff now. And what they're advertising is these really high efficient windows. Some have an argon gas in them for energy efficiency and other things. And so that was one area that technology has caught up with and kept up with. And we're able to use that technology to install better windows and door systems, or what we call fenestration products. Table 40226 under number 53 corrects an inconsistency in steel framing equivalencies. Okay, steel framing is going to have more conduction through the material, the cold form steel material, than it is for wood structures. Now, it's not something we typically see in Minnesota. It's not a common practice, but as lumber prices tend to go up, you may start seeing more and more people trying to do steel construction. As you get into multifamily structures, we are seeing more and more of steel stud type construction or cold form steel construction and things such as that as wood prices go up. Not a common practice, but it's becoming more and more common. And so having a better, a table that basically is more consistent and corrects the inconsistencies, it's good to go. We still require an R20 cavity insulation though. The next part gets into the ducts. We have a lot, the mechanical system, and I tell people all the time, if you're a builder and you don't have a good reputation or working relationship with your mechanical contractor, you should probably develop one, because there's a lot of stuff that they do that affects that building and its performance, sizing of equipment, heat loss calculations, proper installation of ductwork, all kinds of different things. They do the heat load counts, they do the sizing, they do the air conditioner, they do the heat, they do ventilation, they do makeup air, they do combustion air, all these different things. You need to understand and get with them and specifically start talking about things and how they need to get in, when they need to get into this building to do things, and what do they need to do. It adds some new provisions for buried ducts as an optional feature. So instead of, not giving any credit for the insulation in the attic, if you put the duct in the attic floor and then you blow insulation over that, this is an optional feature that the code is now recognizing to give you some credit for. It's not included in the quantitative analysis because buried ducts are not a feature in most homes. They try to keep them within the conditioned space as much as possible. Minnesota, we require an R8 on ducts that are outside the conditioned space, and that has to have a vapor jacket. The vapor jacket is more for the air conditioning season. As you're running cold air through that duct, condensation can happen on the duct, and then you get dripping through the insulation, which deteriorates the R value of the insulation and comes down into the ceiling or through the wall system or wherever it's installed. So ducts that are located outside the conditioned space, meaning outside of the air barrier, whether it's in a wall or on a ceiling, are required to have an R8 with a vapor jacket. Same thing with any ducts that you bury in the attic. Again, they also have to have an R8 with a vapor jacket, because even though it's buried in the attic insulation, you're still going to get condensation, and we don't want that attic insulation to get wet. And so the idea there is to keep the condensation from happening, keeping the duct colder. Warm, moist air can't get to the cold surface of the duct where condensation happens. Therefore, we don't have the dripping, we don't have the problems. And so whether you're installing ducts above in the attic, above the insulation, or if you're burying them in the insulation, our Minnesota code is more restricted and requires 8 of an R value of 8 with a vapor jacket on that duct itself. HRVs and ERV efficiencies and requirements for their efficiency of the fans that they use is there. It should decrease energy use because we're getting a more efficient fan. Replaces the prior efficiency values. It's not included in the energy analysis because it's an optional feature as well. However, these mechanical ventilation systems are not required to be installed in Minnesota. I want to say that again, we are not required to install an HRV or an ERV. The code says you must provide mechanical ventilation. They're commonly used and they do meet our strict ventilation standards, but this is actually a mandate that we won't have to deal with very much because it's more of a mandate on the equipment manufacturers. They're the ones supplying the fan with the unit, so they're the ones that have to provide a very specific fan efficacy for their design when they design these mechanical systems so that we can install them in buildings. So this is one that we won't have to deal with very much in the field, but again, it's on new manufacturing. There may be some HRVs, heat recovery ventilator, or ERV, energy recovery ventilator, out there that don't have the new fan efficiency requirements or efficacy requirements, but the code's not retroactive to make them go back and do them, and it doesn't tell them you can't use them still. It's on the manufacturing of them from a certain time forward. Lighting, high efficacy lighting, again, we went from 75% of the light fixtures or the luminaires of those fixtures, the bulbs, whatever you want to call them, to 90% of the permanently installed fixtures in all the homes have to be high efficacy. So you're going to be looking to see, and you're probably already seeing a lot more fixtures that are designed with LED lighting or another form of lighting that is much more efficient than the typical condensate bulb. And again, a condensate bulb gives off a lot of heat, 400 degrees in heat temperature at the center of the bulb, where you can, you know when you grab onto it, but if you grab onto an LED or a compact fluorescent, it's not as hot. And the LEDs, you can hang on to for a long time before you feel any temperature runs. And so increasing that percentage of efficacy is a clear reduction in energy use. And it's changing across the country. Now in Minnesota, again, our homeowners and our builders are on top of this. This is a fairly simple thing to do. Does it guarantee that a homeowner won't replace the LED bulb with a compact fluorescent in the future? No, it doesn't. But we can't control the homeowner and what they do. That's just part of the business. The homeowner can do what they choose to do, but what's happening is they're starting to stop production of certain condensate bulbs in certain ranges of wattage, because that's the mandate, is that you can't produce them after a certain date. And so eventually you're going to run out of these bulbs. Well, there's probably millions of them on the market right now and out there on store shelves all over. But as you go to buy light bulbs for your home, as you look, you'll find that these lighting section, you're seeing many, many more versions of high efficiency bulbs or efficacy bulbs than you are the compact fluorescents. Are taking up more and more shelf space, while the compact fluorescents and the condensates are actually getting less and less shelf space because the efficiency of these LEDs and the number of times you have to change them, their life cycle and everything else is so much greater. It's just such an energy savings. Okay, the next one is the standard reference design or a simulated performance compliance path. The prior code used a term based on outdated efficiencies, and there's a performance path. So we have, again, prescriptive paths and we have performance paths. It's not included in the quantitative analysis because it is performance. They have to perform to meet the code, meaning somebody has to do an analysis to say that this is meeting the code. And we do see that on several homes, people do that. It only affects the performance option, doesn't affect the prescriptive option. We still see a majority of the homes being done under the prescriptive option, and builders and inspectors just don't understand the intricacies of a performance-based code, so they're not going to that. There are agencies out there and companies out there that are doing some studies on things such as ERI, Energy Rating Index. It's based on an ANSI, ResNet, and now ICC as well, standards. It's a 301 standard, but you have to be trained to do this. It's not just something that, you can just say, okay, we're going to use the ERI. We're good with it because we've designed and that's what it means. Somebody's got to show that work that you've gone through and says, I'm not meeting the prescriptive option. I'm doing more of a performance-based thing, and here's how the building will perform. The building can use X amount of energy. Under our performance office, we're using X minus whatever and creating a better efficient building. And so the energy rating index is something that is done typically by a third party unless the builder themselves has somebody who is generally trained to do this work. It only affects the performance option of the code. And so that's the key there. It's not a prescriptive. You don't do an ERI on a prescriptive building. It's done, it's met the code already. Why would you spend the extra time and money to do this? That's basically that one. The ERI, they've raised their threshold. They were lower. The lower the number, the better here as well. Now they've relaxed that threshold. I believe it was a 51, it's now at a 55. So they've raised it to relax it so that more and more buildings will meet this. And that standard has been kind of bouncing around a little bit. Nobody was really sure where it was going to land and stay. But by strengthening the mandatory and minimum envelope efficiency requirements, it prevents degrading of the envelope, the moisture load issues and other things. And you get to trade that off for something else. Maybe you ended up using condensate light bulbs somewhere else. So you created a better efficiency of the envelope or a window system that's much better than what it was. You can trade things off. And that's what the ERI index does. It says the building is allowed to use this much energy. If you're equal to that or less, and they can prove that during an energy rating index study, then you're good to go. Now, it's a performance path. There is a cost to this, and these costs, I think, have come down since I originally put this program together. But at the time when I called around and asked some of these people, it depends on the size of the home. It depends on how much you want them to do. You want them to do just the design, or do you want them to do the follow-up testing at the very end when they come in and actually do the blower door test and things such as that? And then that also tends to include several inspections that they do during construction to make sure that you are getting the air barrier sealed in all locations, so that you get to the end of the job site and you do your testing and the building fails. Now what do you do? That's the wrong time to know that something went wrong. And so you're now tearing things apart to try to get things to be efficient and meeting the code, where if they're going to design it this way, they inspect to the design that they've given you as a third party doing your energy performance. Doesn't supplement what the building inspector needs to look at, but as a third party company, then they're guaranteeing that you can meet the testing at the end, and they work with you on that. So it depends on what size your home is, what size the multifamily might be. How are they going to test that? Again, as we get into multifamily with multiple wings and things like that, how do I test one townhome unit? I've got to somehow make sure I can close it off from all the others, because there is leakage from building unit A in building one to unit B in building one through the common walls. And so some of the builders that find or call me and say, I got a townhome and I can't get it to pass. And my question is, did you treat the common wall between units as an exterior wall from an air barrier standpoint and seal it? And if they haven't, usually they go back and take care of that, and it's not a very big issue at that point in time. Then it does create a much better envelope, because leaking from building unit A to building unit B to next door neighbors makes your unit leak more, and that doesn't meet your requirements. The next one requires the HVAC systems and additions and alterations comply with the same requirements as a new system. Okay, this improves HVAC efficacy. So if I'm putting in a family room or something like that, the first thing I really truly need to do is look at my current mechanical system and say, is it sized in accordance with the code? Is this going to allow enough heat? If I'm going to use that to supply heat to this new large family room I'm putting on, will the furnace be able to handle it, or will the air conditioner be able to handle it? Now, with a 40% oversizing on furnaces and a 15% oversizing on air conditioners, you might think, oh yeah, it can, but that's not what the oversizing is for. That's a misnomer. People think that, but it's truly not what the oversizing is for. Oversizing of the equipment is for when the temperature gets above or below the design temperatures. Example, St. Cloud, Minnesota is a -20 exterior design temperature. So I'm heating my building up there. I'm allowed to oversize my furnace by 40%, because does it ever get below -20 in St. Cloud? Well, sure, you know, probably almost last weekend. It got pretty cold. I live East Bethel. I south of there, and I had a jacket on last week, and it was chilly. But it's there so that when it gets colder, the equipment is sized to make up for that difference and can properly heat the building. And so that's why we have oversizing. Oversizing is not done. You can't say, well, I'm oversized 40%, so I can put an addition on. No. So the first thing you need to do is you need to make sure that the equipment is sized accordingly with the size of the building that you're having. And if you're putting an addition on, there are many times where that specific furnace and its efficiency, depending on its age and how efficient it is, may not provide enough heat to heat that building. It's got to be, you know, between 0 and 40%. Maybe that 40%, you know, allowed, it fits in there, but that's not the intent of that. So you really do want to look at that, because if you're designing right at the 0 or 1% by saying I'm putting the addition on, I'm still oversized by 1, 2, 3, 4, 5% even, that's just not enough for when those temperatures change. You're going to have cold spots in the building without a doubt. It's not included in as the quantitative analysis. It's outside the scope of the established residential methodology. So they didn't include that in their analysis. It is a code change, but they didn't include it in their analysis. We talked about pool covers and the fact that the requirements for them, and the fact that in Minnesota, we're seeing when we do have pools, we're seeing them get pool covers. I think people are really on to the fact that if they put a pool cover, solar pool cover on them, they can actually heat the water with the solar. And so if they're getting all of the heat for that water and they don't provide a heater to that, even these above ground pools, you know, you put a solar cover on there, as I had one for years when my kids were little and stuff, and they work really well because it really heats the water up. I mean, there were days when I said, man, we should leave that thing off. It's like a bath water. It's not refreshing when you go in. And so we never did have a heater on that pool, but it maintained temperature just due to the solar cover. And that was a site recovery. And we basically had 100% of our energy used for heating that pool was solar generated. Doesn't mean you have to have solar panels on the roof of the house or on the ground anywhere. It could be as simply a cover that is rated for a solar cover that allows heating of the water. And it also is a vapor retarder at the same time. So of the 47 approved code change proposals that were analyzed for 2018 IECC, only 14 changes had a direct impact on energy. 11 saved energy, 3 increased energy, and that's okay. That's okay if that happens. On May 2nd, DOE did a preliminary determination on the 2018 code and said that it will improve energy efficiency in residential buildings. 1.9% energy cost savings. You see, these numbers are kind of low. The 2015 was 0.98% here for total cost energy savings. This is the cost required for the building's functions. So the total over 6 years on that was only just under 3%. 1.9% for source energy savings. As we talked about earlier, when you have the source of, energy required to the building and generation, transmission lines and everything else like that, that's increased again over the 2015 code because of new technology. And again, just under 3 from the last 6-year cycle. And then the one that is really the on-site, what the consumer sees, is 1.68%. From 2015 to 2018, it was only 0.73%, just about 0.75% from 2012 to 2015. So it's just under 2.5% increase in energy efficiency on a 6-year cycle. Now, to get to that 6.5 or that 2.5% or on here in the 6-year cycle, there are some costs associated with it. So where is what we call the ROI, or the return on the investment? Well, as we look at the graphing from Pacific Northwest Labs, you can see they started back in 1975 graphing the commercial energy codes, the model energy codes in 1983. And then 86, they split it into residential and commercial. And the green is the residential line, and the yellow is the commercial line. And you can see the increase in efficiency as we go through here. And as the ASHRAE standard went from 90 to 90.90A and 90.1, it stayed at 90.1, but there's different years on 3-year cycles as we've gone through this, all the way down to 2010. And then in the IECC, in 2000, we went from the 1998 model energy code to the International Energy Conservation Codes. When the International Code Council had their first published codes, they were the 2000 codes. And you'll see there wasn't a lot of efficiency increases between 2000 and 2006. But from 2006 to 2009 and on to 2012, the DOE, Department of Energy, was charged with creating a 30% or more increase in energy efficiency for all residential buildings across the country. So they got very active in things. They got very much into the code hearings, into all the research, into ways to do things, provided tools for everybody to use to make sure we can document this stuff. And you can see there's a dramatic increase in energy efficiency all the way down to 2012. And then again, because we brought all this technology into play, and now between 2012 and 2015, we had a slight increase, but not as much as you would hope for. Again, we caught up with technology. Technology now has to get ahead of us again. From 2015 to 2018, there was very little increase in efficiency, as we've seen, less than 3% increase in efficiency. And so you ask the question, and we get this asked all the time by agencies and builders and owners and everybody else, is to do all of this, what's it costing me, and where's the ROI, or return on the investment? So let's talk about Minnesota's climate zones, and specifically as far as how this is looked at and why we go forward with what we do go forward with, and how we look at and adopt the codes. We take this into consideration. It's something that we do need to do. The cost effectiveness is based on expected changes in construction costs related to the energy savings that were analyzed for these two climate zones, Minnesota's climate zone 6 and their climate zone 7. And it's based on the analysis done by DOE's established methodology for the International Energy Conservation-based codes. They evaluate 32 different residential prototypes. It consists of 2 different building types, 4 foundation types, 4 HVAC types in each of the 2 Minnesota climate zones by simulating weather data. We've got research facilities in Cloquet and Rosemont that can research, that we used when Dr. Goldberg did the research for us on our building durability research study to simulate southern and northern climate zone Minnesota and how those foundation systems will perform. They utilize those agencies as well in those facilities. Minnesota climate zone in the 6th, the southern climate zone, is based on Minneapolis-St. Paul data. And for climate zone 7, they utilize the data from Duluth. Again, here's the current climate zone map. This is going to be changing a little bit here as we get into the 2019 ASHRAE document. Not sure if the IECC went there or not, but the ASHRAE did, and that's for commercial buildings, and that's where we're currently reviewing. Stay tuned for information further on that when we get final decisions. But the current Minnesota's foundation has a research study that we have to do every time for a durability standpoint. It's got a trade-off that allows a reduction of foundation wall insulation from the research grant that showed the study and the research that we did showed that you need an R15 on the exterior of the foundation. So there was a proposal and it got passed through that there could be an R10 if the tested envelope leakage was less than 2.6 air changes per hour at 50 pascals of pressure. So essentially, the code would tell you an R15, but then in 402.2.8 of the residential code is the exception that says if your building passes an air change rate of 2.6, which is 0.4 below the 3.0 for a 15, then you can go with an R10 on the foundation wall. But it's got to be on the exterior side. Because of the durability issues that we have is the reason for that being on the exterior side. It results in a modest net energy savings in the affected buildings, those that have heated basements. It was not assumed in the cost effectiveness because this was one of these things that came on very late in the process of this adoption. It was placed in the code near the end of the adoption process, has not been included in the foundation durability study at that time because the study was completed. It would be in the next one if we do when and if we do that. And so based on the Minnesota statute, if we change to a new energy code for residential buildings, as we haven't, the last cycle we did not, we stayed where we were because the increase in efficiency wasn't enough to offset the cost. And so if we end up finding technology that's there that says, yes, we need to update our residential code and how we do things, then we will end up doing a foundation study again, which will include it. And it was there for a couple of reasons. One, for an energy efficiency reason, but two, for a durability reason. And durability was probably the bigger of those two reasons, in that we were having problems with moisture in walls, in the basement walls. We were getting many, many calls on, green looking mold that's kind of slimy looking in the corners and things like that, which could be penicillium or spirea and things such as that. They're just not good to be breathing in. And so the foundation research had to address moisture loading on foundations, and that's what it does. And it does it very well. Now, the very positive thing on this is after the fact and all of this came in the radon provisions of the code, where we are now ventilating the soil gas of radon from beneath and around our foundation system. Well, interestingly enough, in and or below, I should say, and around that foundation system, there are other gases in the soil. There's methane, herbicides, pesticides, and a real big one called moisture. And when we're ventilating that soil gas of radon out, we're also ventilating all of those others out. We've seen the drying of basements increase by 50 to 60% in many homes once a radon system has been installed, because it also takes care of things beyond radon. Sure, it gets rid of the radon gas, drops those numbers in a very good fashion and does a great job of it, but the moisture loads on these homes we've been reported as being less and less smell from them, from that damp smell you get or anything such as that. And so the trade-off of this is actually reinforced by the fact that we've also did one additional thing in adding the radon system. Has really helped this trade-off in the case of moisture issues, and actually has helped the entire code. Even if you had an R15, putting a radon system in and depressurizing that subslab area is a really good thing because it gets rid of the moisture, which is a very big positive from a durability standpoint. Let me make a computer change. Oh, sorry. So wood frame wall R values. The 2012 IECC required 20 plus 5 and a 13 plus 10 climate zone 6 and 7. Okay, we didn't change from the 2012 on the residential energy code. We have the exact same energy code as that for the 2018 version. Verbatim, line item per line item. So it's basically the 2012 code moved forward without any changes because the efficiencies of the going to the 28 and the cost factor didn't offset. We had some differences there, so we stayed with what we had. So when I say 2012, it also means a 2018. So it requires a 20 plus a 5 in the national code or a 13 plus 10, depending on your climate zone. We amend that to an R20 or a 13+5. And then that's climate zone 6, the southern climate zone. And then in the northern climate zone, we have an R21 climate zone, or R21 for that climate zone in the colder areas. We kept the cavity insulation only option for two main reasons. The residential industry was just not ready to address the complexities of flashing exterior openings to foam insulation on walls with systems that will keep the water out. We still see some challenges time to time, even on some commercial buildings where we have design professionals involved and things such as that. But on the residential side, we just, the industry is moving so fast and things such as that. They do a great job in building our buildings, but the complexity of installing flashings and fastening them to foam insulation around window and door units and extension jambs that got to be extended out and other things, the industry just was not ready for that, and they told us that. And the other thing is the majority of the builders wanted to keep a cavity-only option. They like working with the cavity-only option. They've realized what they have to do from a standpoint of vapor barriers and air barriers, and they've kept that option in place, and they know how to do it. They're doing it effectively, and they're getting durable buildings with everything else that is into this, including the radon and the foundation research study and everything else. And so they wanted to keep that option. We heard from them. We respect that. We listened to them, and we've kept that in there. Now, nationally, the code is going back from going away from a cavity-only option to going back to a cavity-only option because the builders on the national level made their voice heard as well, as did a lot of the code officials as well. And so what we've done in Minnesota is coming back around to be something that's now going to be an option for across the board, across the country, and across the world that uses the icon. Basement and crawl space wall insulation, that's where we get in to start dealing with the fact that you've got to be able to understand moisture migration, moisture dew point calculations, and things like that. The 2012 requires a 15 or a 19 in climate zone 6 and 7 respectively, with the insulation extending to the finished floor 8 feet for basements. The Minnesota code says it eliminates the R19 cavity option. The reason we do that is because we knew at the time when this came out, the R19 cavity, the building foundation research showed that the R19 cavity was a bacterial breeding ground and would hold a lot of condensation and moisture. And so we eliminate the R19 cavity, and for the R15 continuous, it requires at least an R10 of the R15 total to be on the exterior side of the foundation. Not more than an R11 can be on the inside. It's all about calculating dew point, and it's based on the durability study that we did under state statute, and we've done it twice, and both times we had the same results. Different methodologies, different testing equipment, different materials came back with the same results. It's a performance of moisture loading. Minnesota code requires basement insulation to extend down to the top of the footing or 10 feet, whichever is less. Now, that's on the exterior. On the interior, we typically see them run an R5, probably a foam board of some type on the interior side that runs to the top of the floor, because when they put the floor in, they've got a radon system underneath there. They have to caulk the edge of the floor to the foundation wall so no air can come up there. And if that's done right and done well, you can put that foam board on there and you're not going to have an issue with moisture condensation and durability issues. And so that's the reason that we allow that on the interior side. Now, of course, using a foam insulation on the interior side, you have to take into account other things as flame and smoke and other things such as that are in the International Residential Code. I believe 316, R316 is the section still. And so you'd have to make sure to take any of that into account depending on the product you're using. And DOE's methodology that they use does not accommodate for splitting that insulation on a foundation. They basically look at it either on the interior or on the exterior. And so they simulated it as a single layer R15. And with conditioned crawl spaces that we have in Minnesota as well, DOE doesn't have them regularly around the country. And so those weren't part of their analysis as well. So when we did our foundation analysis, we had to take those into account too. The 2012 requires R8 on supply ducts located in vented attics and R6 on all other ducts. So when you're running ductwork into an attic, we try to avoid that in our climate zone, but when it has to go there, it has to be insulated with R8. And we learned earlier from the mechanical code, it has to also have a vapor jacket on. Minnesota code requires various values ranging from a 3.3, depending on what the duct is. There are some specific ducts out there that have performances based on them that are designed to be an R3.3 and don't condensate. And so up to an R8, and we add that vapor retarder requirement. The absence or presence of the vapor retarder has no effect on energy consumption based on DOE's methodology. If it's outside the envelope and the conditioned space of the building, it isn't taken into account because it doesn't affect the actual building living area. Ducts outside the building and outdoor air intake and exhaust ducts that are located coming in, and once you get in within the conditioned space, they need to be insulated to an R3.3. DOE doesn't consider these ducts in their analogy, so it didn't have any effect on the comparison, but in Minnesota, we've addressed these because we know the issues. If you're within a cement slab or within the ground, you need to be a 3.5. And again, DOE's methodology doesn't consider these, so they aren't part of their comparison, but we know what we need to do in Minnesota, and we've required this. And many other states are doing the same thing. Attics, garages, ventilated crawl spaces, the same, R8. They don't consider ducts in garage. And again, you can't heat the garage with the furnace from inside the home because you can't have any openings in the garage into the mechanical equipment, because if you have supplies and or returns, it can breathe back in fumes that we don't want brought into there. Spill some gas fumes get sucked back into the return air plenum. When the igniters ignite the flame in the furnace, we've got a major problem with an explosion happening. So you can't put supply or return ducts into a garage, but if your ducts pass through the garage, they still have to be insulated to that R8. If you're inside conditioned space, there is no requirement for insulation. So we're seeing the fact that because of having to insulate ducts that are installed in exterior walls, and the reason they're having to be insulated to an R8 in the wall cavity is because they're outside the conditioned space. The space is typically conditioned with forced warm air moving it around, and you have an air barrier behind the gypsum that stops that air from getting into the wall cavity. So anything in that wall cavity is now outside the conditioned space. Therefore, you need to make sure that those ducts in those walls are an R8. Once you get inside the conditioned space in a common wall, maybe you're running a plumbing wall, 2x6 plumbing wall, and you've got a space in that wall where you can run a supply duct or return duct to the second story. You certainly can do that, and it does not have to be insulated. The ductwork does have to be sealed and fastened together with at least 3 fasteners to prevent hinging effect, but it does not have to be insulated. For mechanical ventilation, the 2012 IACC, it defers you to the IRC on the mechanical revisions, mechanical parts of the IRC, which we don't adopt in Minnesota. So therefore, you would go to the IMC for ventilation requirements based on the 2012 documents. But 2012 does not use the DOE methodology, but it requires the equivalent of a continuous insulation of 60 CFM for about a 2,300, 2,400 square foot home that has 3 bedrooms, single family home, and 45 per dwelling unit on about a 1,200 square foot per unit multifamily home that has 2 bedrooms. Minnesota gives us 2 options for identifying code continuous insulation. DOE's methodology analyzes ventilation only on a continuous basis. We have 2 options. We have, continuous and non-continuous insulation. So we base it on a square foot floor area. So when you look at the ventilation for a home today, you take 0.02 times the conditioned floor area plus 15 times the number of bedrooms plus 1 for the second person in the master bedroom. You divide that by 2 to get your continuous insulation. And then the total ventilation is the other half of that. So you can come up with the fact that you have 100 CFM of total ventilation, 50% of that has to be run continuously, that much per hour. So 100 becomes of a total ventilation becomes 50 CFM continuous. Now the continuous ventilation has to either A, run continuously at 50 CFM per hour, or you have to you can have a 100 CFM fan and run it at 30-minute intervals, or some other version of a fan that runs at a timer cycle that actually will provide you the same ventilation as if you had a 50 CFM fan running constantly third of the hour. You can put them on a cycler that does that for the continuous, but it cannot be controlled by the homeowner. This is something that just is set up and is run constantly. The only way for the homeowner to shut that off is to unplug the ventilation system or do something to stop the ventilation system, which is just not a good idea. And so we have a little different way of looking at that, in that we have continuous ventilation, and then the total ventilation, the other 50%, is what is controlled by the homeowner. So, you know, you're out there and you've got family over for the holidays, your continuous ventilation fan is working, and you decide that there's a lot of cooking going on, the fireplace is going, and everybody's exhaling and things such as that. Maybe we need some additional ventilation in the area now. That could be something such as a bath fan, another bath fan, could be a hood fan, something that's ventilating air to the exterior. And that one you get to control. That one the homeowner can control the part that makes up the other 50% to get to the total ventilation. The rest of it, the continuous ventilation, is not controlled by the homeowner. It's done and set up by the builder as part of the home system. So in accordance with Minnesota Code and table 40352, based on their prototypes from the DOE, we have 55 and 45 CFM respectively. The analysis assumes lower rates required in the table. And because we require a balanced ventilation, which their methodology doesn't 100% simulate, it's more of a continuous exhaust system than a balanced system, we end up having to evaluate that by doubling the fan energy. We had specific requirements for HRV, ERV installations. Now, these are very popular in our state, in our climate zones, in the cold climate zones, in that an HRV, ERV installation, when they're installed as part of a balanced system, they work very well. There are some requirements there from a standpoint of bringing air intake, you know, from the HRV or ERV as the cold air comes through. A heat recovery ventilator basically brings the cold air from the outside, and it passes alongside of a heat exchanger where the air from inside is going outside. It drops off the heat particulates that are then picked up and temper that air coming in. But if that air is then dumped into the mechanical system on the cold air, return air side of the furnace, you have to make sure that it's at a specific temperature of at least 50 degrees or more, depending on the appliance and the manufacturer of the heating systems, before it hits that heat exchanger, or we're going to start cracking heat exchangers. And then we're going to have carbon dioxide, carbon monoxide issues in the home. So if you're doing that, adding an HRV or an ERV, which is an energy recovery ventilator, does the exact same thing as an HRV, but it also has typically like a moisture wheel in it that will help balance the moisture loads in the house. As the air is going out, it deposits the moisture into this wheel. As the wheel spins around, picks up the air coming back in, it picks the moisture back up and kind of balances your moisture loads in the building. But either one of those, or if you have just a fan intake and a fan exhaust, which you can do, if you're dumping them into the mechanical ventilation system, you have to make sure that you're addressing the temperatures at the heat exchanger. So because neither the IECC or the Minnesota Code require HRVs, we don't require them. It's an option. It's a popular option, but it is an option. They have no effect on DOE's analogy or the comparison that they've done. There are some costs associated with bringing Minnesota Code up to the 2018 IECC, and they stem from all the differences between the 2012 and 2018 editions, plus all of our Minnesota amendments in 2012. For the analysis, the cost differences are between the 2012 and 2018 were taken from DOE's reports on cost effectiveness for new code additions. And they go this way with it. They have a 30-year study period, and the 30 years is based on a typical home loan. 30-year value on the home based on the home loan. They have a life efficiency measure or expectancy measure of about 60 years for that home to remain efficient. The rule of thumb kind of in their mind is that after 60 years, through wear, tear, and degradation of products within the building itself, that its efficiency tends to reduce. In Minnesota, we base that on about 100 years of life cycle of the building itself. They provide a discount rate, which is equal to the interest rate of the loan. They average it at a 5%, year loan rate at 5%. And again, a loan term of 30 years. They take out of there a 10% payment for the down payment. They add a 0.5% for a mortgage insurance. Now that gets eliminated eventually in their methodology after the loan balance is less than 80% of the home value. They have a loan fee rate. They increase that or add that in. And then an inflation rate of 2.52, which may be pretty close, maybe a little bit high. And then they include the income tax rate and everything else in there and what those rates are. So they're trying to establish here, essentially in this first column, they're trying to establish a cost factor and a timeline for that so that they can actually do their analogy. So in climate zone 6, the life cycle cost per dwelling unit, single family, 2653, multifamily 719, and you see for zone 7, it goes up. 3259 for a single family and 750 for a multifamily. The state one there, that's the average of those numbers. Annual energy cost savings. This is in dollars per dwelling unit. In climate zone 6, under the code, $146 for single family, $57 for multi, and $169.65 in climate zone 7. Oops, sorry about that. Now, incremental construction costs, you've got to calculate those in that they go up 556 to 506, 449, and 600, and again, state averages. But when you put all of this together, you've got the life cycle costs and savings of the building at 2792 or 3259. But then you've got in the red numbers, you've got those things that you have to delete from that savings because those are construction cost factors and interest rate factors on the money you spend for the additional construction costs of 543 and 506, 512 and 447. Well, when you average them all out over the life cycle of this building, we're still saving $1,743 on every home in the climate zone 6 and roughly $2,300 in every home in climate zone 7. And so with that, again, we go back to the fact that the average here of 1,505 times the number of new homes built in the state. I mean, talk to one jurisdiction up in north of me yet that said they're anticipating 100 to 125 homes this year. And it's just starting to explode and really build up quickly. And so it's not slowing down. You start multiplying that 1,505 times every new building, it adds up very quickly and it becomes a huge cost savings. That's my favorite photo of the whole program. And hope you're not this person. So I guess we finished up pretty close, about an hour and a half. Ben's got some things that he wants to chime in here with, and then I think we'll probably open it up to questions, right, Ben? This is my contact information. You feel free to give me a call and leave me a voicemail or send me an email, and I will get them voicemails and emails. And I'm pretty good at returning my calls. I've got a lot of going on, like everybody these days, but I usually get back to you in a very timely manner. Ben, this one's all yours, buddy.
All right. Thanks, Don. Thanks for your presentation today. It's always great to hear from you. I just wanted to take a couple minutes before the Q&A to connect some of the things that you talked about to stuff that Fresh Energy is working on. So you mentioned briefly that the department is going forward with the adopting the 2019 ASHRAE 90.1 model code. So that rulemaking is about to get started. The technical advisory process took place earlier this year, which was led by Greg Metz, and the Construction Codes Advisory Council will be meeting on, I believe, May 27th on kind of whether to move forward with that. Also, as many of you may already know, Fresh Energy has supported a code advancement bill, which would put our energy code, our commercial energy code, on a 3-year cycle that Don also mentioned instead of a 6-year cycle. And that bill's currently included in the House Commerce and Energy Omnibus bill that is going to be debated next week. So we're hoping that's moved forward with the negotiations between the House and Senate as the session kind of winds down. One more thing that Don mentioned as well is that the 2021 IACC is out, and we have been encouraging the department, Don and his colleagues, to move forward with the residential provisions, knowing that we kind of skipped it last time around, and this update is likely to offer more savings than the previous version. So we're hoping that goes forward. So just to keep it short, to allow a lot of time for questions, happy to dig deeper to specific policy and legislative questions during the Q&A, but thought we could move forward with that. So let me pull up questions. We have a number of them already and get going here. All right, sorry, I'm just getting my screens organized here.
You want me to stop my share on my screen?
Looks like Joe's already done it, so
Okay,
we are
perfect.
good
Thank
to
you.
go. All right, so we'll start with a question from John. It was stated that the 2019 ASHRAE standard was found to improve energy efficiency by a little over 4%. Is there a cutoff level for requiring the use of the new standard? In short, will the TAG recommend moving forward with the 2019 standard or staying with the current one?
I can answer part of that, and Ben, you were more actively on that TAG every time than I was. I'll let you answer the back half of that. But no, the department does not have a very specific, we have to be this or we don't do anything. We do look at every document that comes out on this, and we review it, and we just do our due diligence. That's really what we're there for, is to make sure that if it's, as we've been going on a 6-year cycle, we always have that in-between cycle that doesn't get adopted typically, that we still do take a look at that from an energy standpoint and analyze that and make sure that there's nothing glaring that came out that we think, wow, we really need to do this or not. And we do analysis of that. There's no set number or percentage that we say it has to increase. Again, it's getting tougher and tougher to get those increases, from years back in the double digits and 30% between 26 and 2012. To get them 30%, we're down, under 2 to 3% now. And again, when technology improves and other products are out there that can help us create that efficiency more, again, we want to look at that, and we certainly do look at that. As far as the TAG group, I don't know what their intent is. I think they're going to send it through Construction Codes Advisory Council meeting and get a recommendation. Am I correct?
Yes, yeah. My experience on the TAG is that it is going through that process. I've also given Greg Metz, the TAG leader, the opportunity to unmute himself if he'd like to chime in.
Hey, this is Greg. So I just our intent is to move forward with adopting the next ASHRAE standard, the 2019 version of the 90.1. But again, it's up to, we're making the recommendation to the Construction Codes Advisory Council, and it's really up to them. And they make a recommendation to the Commissioner of Labor and Industry. So it's certainly not a done deal for what we discussed with the TAG, but they take our recommendations pretty seriously. So we'll see where it goes from there.
All right. Thanks for chiming in there, Greg. Next question from Jesse. Has there been any conversation about a Minnesota amendment mandating continuous insulation in residential energy? I know you touched on this briefly, Don, but maybe guess can hit the nail on the head to answer this directly.
A continuous insulation on I'm assuming above grade walls. That's a design feature that the builder gets to make the choice. I don't know of any states off the top of my head that absolutely require continuous insulation or staying with requiring continuous insulation based on the code. What happens typically is if you get a builder who's been doing cavity insulation, and in some of those states where they just adopted the IECC provisions as written that said you had to do continuous, they would switch to a performance option and still keep the cavity insulation in. And again, there's very effective ways to do that, and those buildings can perform very, very well. It's just paying attention to the detail. And even if you're doing continuous insulation on the exterior, again, is paying attention to the detail and making sure that you're keeping that bulk water out. Window flashings at the bottom of windows that, the J channel that comes along the side of the window. How are you getting that water from the bottom of that window to the outside of the side? Simple things such as that to keep that water from running behind that and getting behind the paper or the house wrap or the foam insulation where it gets trapped and against the structural sheathing. So there's a lot to it. It's a lot more complicated than just saying, hey, look, we understand thermal bridging and stopping that heat from the studs from the escaping is a big issue. Yes, it certainly is. But there are other issues that when you do that, what other issues do you actually bring up? And so we try to look at all of them when we make our decisions. As my knowledge right now is we're moving forward with the energy codes the way they are. And I believe we haven't talked recently about going to a continuous only. My guess would be that the builders groups now would really want to keep where we're at.
All right. Question from Kevin. Regarding the residential building shell, efficiency, oh my gosh, and storm caused power outages. Sorry, I stumbled a little bit on that. What iteration of the energy code addresses shelter in place resiliency with days with minimal and maximal outdoor temperatures that go beyond standard energy use metrics? So I guess to clarify, I think Kevin's asking about extreme events resulting from
Sure.
kind of climate extremes, both on the hot and cold end of the spectrum.
And the energy code doesn't really address that. I mean, certainly if you're in some part of the country or the state that you're in, wherever that might be, and you're living somewhat off grid where you're utilizing nothing but renewable energy, you're certainly going to have something as a backup, a generator or something like that to run the essentials, your refrigerator, freezer, your furnace if it's in the winter time, something that would accommodate that. The energy codes are there for everyday use. It's difficult. For instance, even we designed in Minnesota for a 90-mile-an-hour wind speed. A tornado comes through at 120 miles an hour. We didn't design for that. We designed for the average, and that's what we do on the energy code as well. We don't design for the worst case scenario that could ever happen because, in all honesty, the cost of housing would be just astronomical low to be able to buy a house. And guaranteeing that nothing will ever happen. And having gone through a tornado event myself on some property that I have, I can tell you that it's a mess to clean up with. And afterwards, I get it. And I wish that I would have done some different things, but it's well beyond the aspects of the code, and the cost factor is just so high. So the energy code does not look at that. It looks at the average everyday home and the average everyday use.
Okay. Question from Rebecca Olson. If the savings potential is so high based on the PNNL analysis of $1,500 a home, why wasn't the 2018 residential code passed? Were there other factors that played in the decision other than ROI?
Right. And again, hi, Rebecca, it's good to hear you asking questions. It's a big picture thing for us, and we weigh everything into the mix. I mean, we look at what we're doing, what the efficiency increases are, what the costs are, and we have to come up with a determination of, are we going to adopt the new code or are we not? And at the time, because of the statements that we did talk about with that the 2018 wanting to go to continuous insulation and so all the issues that again, outside the scope of just energy. By increasing that energy, are we creating durability issues and things? That's what the department takes into account, and we have to be accountable to that side of it as well. And we do look at that, and I think pretty much everybody knows we're an open book. We let anybody comment and tell us what they think, and we respect that and we appreciate that as well. It's just that when the final decision comes, we have to make that decision, and it's not simply on an ROI. There's many other things that do play into this, and we just don't have time to get into all of them right here probably, but it is not just an ROI decision, no.
Okay, question from Tim Mans. Can air curtains or air doors be used in lieu of vestibules?
Good question, Timothy. Yeah, they can. They're not very effective in Minnesota. There's a couple of, I believe Target Corporation tried it on some of their buildings, and they found that in the really cold days, to keep that energy in and the cold air out, they had to increase the air curtain volume of airflow tremendously, and it was creating havoc. And let's just say if you had a wig or toupee, you wanted to stay away from it for one, and other things, blowing things out of people's carts as they would go out and things such as that. That it's really an analysis that has to be done by the building designer, and most of the time we're seeing vestibules installed.
All right. Couple questions on rain screens from John and Kevin. Is there a requirement for a rain screen beyond a reservoir cladding system on the residential side?
That would be an IRC question. I mean, the code does require that you have a WRB or weather resistant barrier. Rain screens installed behind siding, certainly people can do that. There are systems out there that can be very effective. I think the biggest thing that a person wants to understand is water management, and like we talked about, having good head flashings over the windows and doors and things such as that come up more than 3/4 of an inch, in my opinion, but they should come up a little bit further. But the other thing is manage that water, because water that hits the head flashing runs to the side of the windows. It runs down the J channel. What happens at the bottom of the J channel? Where does the water go? Any kind of an opening you have where the water comes down to the top and runs to the sides, when it gets to the bottom of that opening, whether it be a mechanical opening, window, door, whatever, how does that water get to the exterior of the cladding? And that's really what you want to address, is getting that water to the exterior of the cladding and away from the structural elements of that building. And if you can do that, and there's usually pretty simple, inexpensive ways that use some scrap material to make that happen. But it requires a training, and it requires the due diligence of the installers to do just that. Because once it starts getting behind there in a bulk situation, it goes at a 45-degree angle down and out, and it can actually deteriorate the wall to a point where it becomes a structural concern.
All right. So to the question, I guess, building on that, to the question of training, what about funding for building science training for local inspectors so they can answer buildings questions on why this is a benefit to homeowners and their business? A question from Larry.
The department is offered numerous training. I've personally done a lot of them, but we do a continuing ed training. We have had a spring seminar here just recently on some things on decks that Rich Lockram did a really nice job with, and then Herman Hoglid did one on manufactured structures and some things there as well. And so we do offer training. We also do have many people who send in other training things, and Fresh Energy and Midwest Energy Efficiency Alliance and others hold classes that are accredited through us, and continuing ed credits are given to the individuals attending them for certain licenses. And so if somebody is looking for a one-stop shop to get all your code training, I strongly suggest they look at a couple of places that they could get it, just due to the fact that we're a 8-1 agency, but we can't cover everything every year for everybody. And we try to do things that are pertinent and hot. We're looking at different things, and I know the education section, the former section I was with, is doing a really good job of setting up future classes, and we went online stuff, and we're hopefully going to get back into some face-to-face classes. It all depends on the pandemic things and what's happening there, but there are many options out there. You can go to our website and look up whatever kind of training you're looking for. for whatever kind of license you may have. And there you will find classes being offered both online, webinars, and as well as face-to-face classes that are starting back up now. There's numerous ways to get that continuing ed training. As far as funding, I don't get into that side of it. That's outside my wheelhouse, and I just don't get into the funding of it. Our managers and supervisors provide that information for us.
All right. Question that I'm particularly interested in from Joanne on 1.5-story houses. Could you please explain how we should handle existing home that is 1.5-story with a conditioned bonus room on the upper level and crawl spaces on the side of the bonus room? Should the crawl spaces only be insulated, or do they need to be ventilated? Would you refer to the insulated code section of unvented attics, R 806.5?
Yeah, R 806.5 is what used to be called hot roofs is now called unconditioned attic assemblies, and it's very, very specific. If you have an unconditioned attic assembly, and these you typically have the bonus room. You've got the 3 different areas. You got the peak above the bonus room that is typically a small, short little attic space of a triangle type shape thing, and then on both sides of the bonus room to the outside edge of the walls of the building below, you've got another one. Ventilation is an important thing there. The code actually allows you to ventilate, 1 to 300 if you've got ventilation at the top of that space and at the soffit of that space. And if you can only get it in one location, you can still do that. It requires 1 to 150 at that point in time for ventilation requirements. If you're going to be insulating them, certainly and not venting them, take a look at 806.5, and that's going to be very dependent on what you're using for insulation. If you're using a permeable insulation that allows air and moisture movement through it, you're going to have these requirements. If you're using an air impermeable insulation, spray foams and things such as that are air barriers on the underside of a roof deck, there's a whole different gamut of things you have to do. And then, of course, making sure if you're using foam products, what their reactions to the inside environment, how do you hold that in place? People who want to use bad insulation have to put something on the attic side of that bonus room wall to hold it in place. And so the code does address this. I think there's opportunities for that. I'm a fan of ventilating those spaces. I just think the durability standpoint of it is much better, but the code does allow either or.
Okay. Another self-interested question for me from Larry Mayer. I know, Don, I emailed you about this a year ago and wondering if the recommendations are more clear. Comments on ventilation rates to deal with COVID-19 or just general increased consciousness around ventilation in buildings, around health and wellness and the spread of viruses.
Well, ventilation rates in buildings are there. I mean, years ago, we used to ventilate them by opening windows. Nowadays, I mean, we've had ours open and a lot of people have, but a lot of times people go from heating on Friday here today, and tomorrow they're going to turn on the air conditioner, never to open the windows and things. And, you want to get good air in, bad air out. It depends on where you're at. If you're right next to a freeway, you're going to probably open up certain windows and not others. But ventilation rates and the COVID, there's no real specific thing in the building code that would address these kind of situations. I think there are ionization systems that can be added to mechanical systems, and as those become more and more prevalent, and we start seeing new systems and things like that to address these kind of pandemic issues that we have, we might see some changes in the codes to accommodate that. But I'm guessing that's more for commercial buildings such as schools and hospitals and nursing homes and things such as that. I doubt you're going to get much going toward the residential side of it very soon, but I could be 100% wrong in that as well. I think there is ionization systems out there that can help with this, but as far as how much and when, that's not determined yet that I know.
All right. Another question from Kevin. When an ERV or HRV is installed and powered off by the homeowner, what is the acceptable percentage of operating airflow that the connected air handler can pull into the duct systems from the HRV intake and exhaust dust before the interlock dampers are required per code? Very technical question.
Well, so did he say powered off or powered up?
I believe powered off.
So a homeowner goes in and basically unplugs. I mean, ultimately, the mechanical contractors would love to actually hardwire that thing into an outlet so the homeowner can unplug it, but that voids the listing of the appliance because it comes with a plug-in. And so you can't do that and legally install it. And so the ventilation is important. The minute you shut that ventilation off, your dampers and everything are, I mean, the performance of them, every bit of that's out the window. They're designed for certain things, and the dampers are designed to open and close during, defrost cycles and everything like that. And it's a design system. And I guess I asked the question back when people ask me these kind of questions is that you're going to dive into the water way down. Are you going to, shut the tank off when you're still, 30 fathoms down, or what are you going to do? You're not going to do that. You don't want to shut your ventilation system off. Homeowners seem to think that running the fan on the furnace constantly, I do that at home here, and it's a DC motor on the fan. It's run on energy stored in the furnace system. If I didn't store it in a battery DC system to run the fan, it would get wasted anyway. So I'm actually making use of it. And the efficacy of these fans and the efficiencies of these fans are so much greater than they ever used to be that they don't take a lot due to centrifugal force to keep that fan going. The same thing happens with these systems here. Running these fans, they're so efficient, and you're seeing them going to, variable speed drive fans and things such as that are even more efficient. The energy use there is a little bit of additional energy use there is very much offset by keeping that building drier, more durable, healthier for all of us. And at some point in time, somebody's going to say, when are we going to start bringing into the codes, keeping the occupants healthy? Like on residential codes, like we do on commercial codes with ventilation rates and things there, depending on the occupancy. And so, we address that every day with ventilation in the building codes. But as long as you've sat down and actually went through and sized your equipment based on your heat loss and cooling load, and you actually go in there and you put a good ventilation system in, you have a good makeup air system, and your combustion air is addressed, you shouldn't have many issues with your building. Now, the big key factor on that is maintenance. I can't tell you how many times I've gone to a home where people say, oh yeah, we change the filters on a regular basis, and I open up the HRV or ERV and there's the instructions are still leaning against the filter that's clogged. They didn't know that was there. And I tell builders, go back to that home 3 weeks after the homeowner lives there and do a walkthrough again with them, because during the day of closing, they're not worried about what you're telling them. They're worried about other financial things for closing. How much money do they need down? Did they go over on this? Did they do that? They're not paying as much attention as they will 3 weeks later. As a former builder, I used to do that. It was very effective.
Yeah, I've heard you say that before, and I think it's great advice. Couple more questions. Hopefully we can get them in before we run out of time here. To paraphrase a question from Artie related to continuous ventilation wasting energy when residential unit is unoccupied. How does continuous ventilation work for unoccupied units?
Well, the ventilation system is not only for the occupant. It's for the building itself, and it gets rid of, when an occupant is there, the ventilation system is getting rid of carbon dioxide, carbon monoxide, any other VOCs that might be in the building and things such as that, and moisture. And if you have a new building and it's operating and you go in and shut the mechanical systems down, as most builders will tell you, that all of a sudden they start getting a funky smell in there because the moisture loads start to increase. And so, fortunately today, these homes don't sit completed and empty very long, and people are in there and they're running these systems and doing what they're supposed to do. The little bit of energy use on a continuously ventilated building, remember, you're not using the total ventilation button because nobody's physically in there to turn that one on. That little bit of energy that runs here and the centrifugal force of the fan as it goes around, and the efficacy of these fans is so minor that it's offset greatly by the mold, mildew, and moisture issues that are probably going to be caused.
Okay. Couple follow-ups on ventilation. When the ERV or HRV is off, code stipulates a performance standard that requires interlock dampers. What does this flow verbiage assume? And also a follow-up on ventilation fans. do we bring in significant cold air during the winter with these running?
Well, and I'll stress the second part. The first part is very difficult to tell you, yes, this is a number, because one, I don't know the size of the building and what they're using for ventilation, exactly what the size of their HRV, ERV is. Are they utilizing exhaust only systems as well when they need to, such as the kitchen when you're cooking and running a vent, a vented hood to the exterior. So that's a very difficult one to say, put a number to that. It's hard to do that without actually sitting down and running the numbers on the building. But as far as, the system and working, it just brings in a lot of cold air. Certainly it does. And that's the advantage of an HRV or an ERV, is that it somewhat tempers that air. It's you're using the energy and the air that's going out of the building to temper that air coming into the building. Is it 100% trade-off? Probably not, but it's certainly substantially better than it ever was. Years ago, people would say, well, I never had to have these things in my home before, and it was really dry, but it also leaked air, like crazy. And a lot of air would go out of this building when it's pressurized, or the positive pressure inside the winter. The heating bills are astronomical compared to the buildings of today. And if you're going to make these buildings of today as energy efficient, says we have to, under federal law, we have to ventilate them. And whether it's occupied or not, you should have some ventilation going in that building.
All right, I know we're close on time, but I think we have one more quick one before we wrap up. What about poly under the slab and insulation under the slab? What are the requirements now? You may have gotten to some of that later on.
Yeah, the code requires a 6 mil poly underneath the slab, overlap 12 inches. Doesn't require it to be sealed in the overlap and things such as that. It's a vapor retarder for the underfloor. Both residential and commercial buildings have that. If you're using foam insulation under that slab, you certainly can use that if the foam has a perm rating to it of 1 or less. The challenge is as you put foam under there and you step on it to move the concrete around, it tends to break. So now you've got cracks in that have to be addressed, and every seam in it would have to be taped or caulked together. And so it becomes an issue. If you're doing insulation under a slab to keep the moisture out, you could probably do it much easier with a piece of poly. And most of the time when they put foam down, they have poly underneath that anyways. When you're doing concrete finishing, the concrete contractors for a while were cutting holes in that thing because they didn't want the concrete to take so long to finish up. Well, you use a little air entrainment in that concrete and some calcium chloride, and that concrete's going to finish just like there was no poly there. So there's ways to make that happen and make it happen effectively. If you're putting a heated floor system in, like a radiant heat system in a floor, absolutely you should be putting at least an R5 under there, 1 based on the code and 2 based on manufacturer's installation instructions of their system. They want that heat going up because that's what it's sized up. Oh, sorry about that. The advantages of working from home.
All right. Well, I think we've made it through all the questions, and keeping an eye on the time, I wanted to thank everyone for joining today, and special thanks for Don for presenting today. I learned a ton today. It was a wealth of information. Attendees, please feel free to follow up with Don with any additional questions with the contact information he provided. You'll be receiving an email from us early next week with a link to the recording of the webinar. Thanks so much.
And you guys are putting this out so that it can be video watched, correct?
Yep. The link will be included in the email, and it will be hosted on Fresh Energy's YouTube page.
Okay.
All right. Thanks so much. Everyone have a great weekend.
Take care, everybody. Have a great weekend.